the one of the task or the goal for our team is to provide sample solutions, so you can go there and download and quickly have a look at some code sample. So I'd like to point out there's two sample solutions. One is called Automated File Uploader for BigQuery. So if you download this sample application, it is a Google App Engine application. So what it does, it actually create a object change notification to a bucket. So whenever you put, say, a file that's ready to upload to BigQuery, the App Engine application will automatically pick it up and use the API, the BigQuery API, to upload it to BigQuery. So you can, if you download that sample application, you can see how the object change notification is done and how you can use the BigQuery API to upload from App Engine to BigQuery. So the other sample application is called using ETL2 on Compute Engine. So this is a script. So if you download the script will automatically create an instance, a virtual machine instance on Compute Engine. It will install all the necessary software that you need to run a ETL2. Oh, just refresh it. So I just add this like a, so if you refresh your slide, then you'll see them. So it will, so ETL basically is extract, transform, and load. So there's some open source tools for you to do run ETL to transform your data before you load it to BigQuery. So you can download that and see how you can look at the sample and see how it create a Compute Engine instance, install all the necessary software. So the software that is installed include the ETL tools, VNC server, so you can have a graphical interface to run your ETL jobs. So then this session is going to be on advanced topic for BigQuery. So we're going to look under the hood. We're going to look at the Dremel architecture. So as I think we mentioned earlier, BigQuery is based on Dremel, and Dremel has been used internally at Google for a long time. And we're going to look at how to build end-to-end solutions. Okay, so before we dive into the Dremel architecture, so let's just take a step back and look at BigQuery and what's the difference between BigQuery and MapReduce. So the MapReduce, I think the number one difference between MapReduce and BigQuery is MapReduce is kind of like a batch job. So you have to submit it's a batch processing, right? So you have to write your mapper function, your reducer function, and you have your data set, and then you just run it. So the problem is when you run a batch job, there's always a latency. So it's not real time. So if you just run depending on the size of the data set, it can run half an hour to even 2 or 3 hours. So for BigQuery, it's near real time. So it's not really real time, but it's near real time because all your data set is there already. So you don't have to run any mapper reducer. So the latency is much lower. And the BigReduce has the SQL query, which is much nicer than having to write your own mapper reducer functions. So the difference between BigQuery and database NoSQL or NoSQL data store. So the key difference is the NoSQL data store are designed for transaction. So it's optimized for a lot of read, a lot of write, a lot of updates. Whereas BigQuery is a read-only data, so you cannot really update. You cannot run a SQL statement to update one row of your BigQuery, and so the BigQuery doesn't have index. So all your when you upload data into BigQuery, you don't have to specify. Okay, I want to create this index here, index there. So, but whereas for NoSQL data store, you have to specify index. So index is the way for NoSQL data store to perform fast lookup. Okay, so BigQuery is actually based on a concept called columnar storage. So if you look at the diagram here, so for the traditional relational database, so you have a record-oriented storage. So if you create a table, the table has rows, right? So the rows itself is going to store as a single record. So if you look at it, it's going to have record, record, and record, record. Each record has all the data in that row. For the column-oriented storage, so what we do is we break the data down and we store it just by the column. So, and then it's just column, column, column. So it turns out that if you store your data just by column, it offers a better compression ratio. So because most data within the same column are going to be similar, right? So for example, like age. So if you just look at age, most likely maybe someone will have the same age. So that's one of the key difference between a relational database versus BigQuery. Well, I can't give you a number because it really depends on your data, right? So, but yeah. Okay, so now let's, okay, question? Yeah. Oh, no. Okay, the question is, okay, so if you store things in the column, at some point you still have to compose them back into a row, right? So what is the mechanism for doing that? So this is going to address that. So. Oh, the other thing that I forgot to point out is in this previous slide. So, okay, so imagine if you have a table, right? So just 3 columns. If you just say select column A from this table, for the column-oriented storage, all you have to do is to just get the data for the first column, whatever, right? So whereas for the record-oriented storage, you have to get the data for all the records and then just extract it out. So in terms of I/O, if the column-oriented storage is actually much faster. And for a lot of like analysis, like for example, log analysis, right? So most likely you're not, given a web log, right? You may have 200 columns, and most likely you're going to query just 1 or 2, right? Maybe you're interested in IP, maybe IP address, or maybe you're just interested in the country code. So if that's the case, the column-oriented storage actually is much better than the record-oriented storage. Okay, so back to this Dremel architecture. So, BigQuery has this concept of hierarchical serving tree. So if you look at the bottom is where all the storage, where all the data is stored. And then above that, you have the leaf nodes, what we call the leaf nodes. So these leaf nodes are going to get the data from the storage, say, and then we have this long-lived shared serving trees. So all these leaf nodes are actually shared. So we have a pool of machines running as a leaf node, and then they all get requests from different people, and then they'll do all the jobs. So above the leaf nodes, we have what they call the mixer. So mixer basically get the data from the leaf nodes and then do what they need to do. I will have an example following this slide that will explain better. And then on top of that, you have further mixer. So basically, leaf node get the data, do whatever they need, pass it up to the mixer, do whatever they need, and pass it up, do whatever they need. So the key that I like to point out is, in terms of a lot of like query, right? The bottleneck usually, or most of the time, is on getting the data. Like computation is very fast, right? Is the I/O is the slow part. So the goal for this architecture is we limit the I/O just on the bottom layer. So only the leaf node are doing all the I/O. So once they get the data, they just pass up to the mixer. And from that point onward, none of the mixer will need to get data from the disk. So that's part of the reason why Dremel can be so fast. Oh, there's more. There's more. Okay, let go through the general architecture with a sample query. Okay, so we have a sample database called natality. So what the sample database is basically a record of all the birth in United States. So if you look at one record, it will say, okay, this is the date where the baby was born, his gender, he or she, is gender, okay. Maybe whether the mom smoked or not. So we have those records. So this very, very simple query, just say, okay, select the state and count babies from this database between the year 1980 to 1990, group by state. So basically what it does is look at between 1980 to 1990, how many babies are born in what state. So very simple, right? And limit 10. So if you look at, if as a user, if I run that query, so internally what does BigQuery do? So now you can see here. Okay, so the query says select date and year, right? So the leaf node has to get all the data about the state and the year from this dataset or table. Okay, so once the leaf node get the state and the year, so what it has to do is, okay, it has to do group by the state first, right? So whatever subset of data that the leaf node got, it has to do this group by the state, and then it has to run the condition where year greater than 1980 and year less than 1990. So each leaf node is going to take a subset of data. It's going to say, okay, for this column, for this two column, right, state and year, is it between 1980 and 1990? If it is, so I will keep counting it. Okay, so once each leaf node will do its job, right? So looking at a subset of data, and then from that point, it's going to pass up to the mixer. So what's being passed up to the mixer basically is just a record of state and the number of baby that was born in that state for that leaf node. So the mixer would get a bunch of data from leaf node. So the mixer one in this case would have to aggregate count star group by state. So basically just combining data from different leaf node. And then the mixer will pass it to the top mixer. So the top mixer would just do the combining from all the mixer, the first level mixer. And then the mixer 0 has to do the last step, right? So it has to say limit 10. So, and order by count babies descending. So now the mixer 0 has all the data. So it can make the decision to, it can do the ordering and it can do the limiting. So that's how it works. Is that clear at this point? The bottom, oh no, wait, hold on. Oh no, you don't have to, because you just need to know. This will tell you the number of birth, right? So. Okay, so now let's look at a little bit a more complex query that shows you the multi-stage query. And for this query, we actually introduce another one. Complexity is group each by. Okay, so I'll give you a minute to look at this query, and I wonder if anyone can tell me what this query do. So for this query, we are looking at we're querying against the Wikipedia dataset. So the Wikipedia dataset is very simple. Basically, it's a log of who added what pages in the Wikipedia. So it has it's given a row in the data in the table. So you will have, okay, this is the page. What page? Who's the person who make change? So. Okay, so this gives you the count of who contributed the most. Okay. Okay. Huh? More like what? Okay, so I think the guess says, yeah, I think it's right. So basically, okay, let's break this down a little bit. Okay, so let's look at the inner select first, right? So the inner select, we said select contributor ID, so who contributed, right? And then this one here is a little bit complex. Integer, parenthesis, log 10, and count star, log edit. So what it's doing here is basically we are looking at a person, contributor, right? And then we want to see how many times he make modification to Wikipedia. So that's what the count star would give you. So if you just say select contributor ID count star, from this one here, it will tell you XYZ make 500 edit, ABC make 2,000 edits, right? So what the log 10 does is actually we want, because if you look at the number of contributors that we have and the number of edits that they have, is going to have lots and lots of data. So basically what the log 10 does is you bucket people into different buckets. So say if someone make 100 edits, so log 10 of 100 will give you 2. Okay, so if someone make 111 edits to Wikipedia, log 10 of 111, it will give you 2 as well. So, or 2 point something. So the integer will basically chunk it down and make it 2. So basically what we are doing here, we are grouping the contributor. If you make between 100 to 900, they end up in the same bucket. So, and then if they make 1 million, between 1 million and 1, they end up in the same bucket. So what we are doing here is we just want to see how many people make roughly how many edits. So, so. Okay, so if you look, this is how the Dremel serving tree will look like. Okay, so there is one additional layer here that you can see, which was not in the previous one, is shuffler. So what does shuffler do? Okay, so let's just step back, right? If you look at this query, if you just say, if you remove the group each by, what would that do? Okay, so if you look at this query and say, okay, select contributor ID integer blah 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 log edit from this one and group by. If you have to run that one, so what happened is each of the leaf node has to get the contributor ID, right, from the set of the subset of data that it can get. The problem is we have many contributor IDs. So in the previous example, we only have 50 states in United States, right? So try to imagine if we're trying to fit everything in memory here to make it fast. We don't want to write back to disk. So 50 items is very easy to fit into memory. Contributor ID, right? If you try to fit a lot of contributor ID in memory, at some point you're going to run out of memory. So that's why that's what the group each by buys you. What the group each by does is it introduces an additional step of shuffling. So before even the leaf node do anything, what it does is, okay, so now because it's group each by, so each leaf node is going to say, okay, so now my contributor ID, okay, so if this person is ABC123, right? Okay, I'm going to just ask leaf node 1 to do it. Okay, and then if the contributor ID is say XYZ123, right? So I'm going to ask leaf node 2 to do it, right? Yeah, exactly. So yeah. So basically, so what you're doing is you're reducing the size. You're reducing the size that each leaf node has to handle. So in this case, after shuffling, the leaf node 1 would just handle a subset of data between 000 to maybe 100, right? So the next leaf node will handle all the contributor ID with 200 to 300. So you're essentially reducing the size of contributor ID that each leaf node has to do. So okay, so now after that step, after that shuffling step, everything is happy, right? So now each leaf node will do what they need to do the count, do the basically now at this point, so each leaf node will have a contributor ID and then the log the log 10 of the count. And then from there, you pass it back to Mixer. So it will be very, very similar to the simple query that we did. So is it clear at this point? Okay. Okay, someone brought up a very good point. What if the distribution is very uneven, right? So in that case, your query will run very slow, right? Just imagine you have 1 million records, and then they all say hash to two nodes, right? So yeah. We won't distribute because we're just hashing it. So we just hash it in. Okay, so that's okay. So since he brought up that point, so this is a real life example, right? So there's a company trying to analyze weblog. So weblog, right? So you have users. So what they are trying to do is they're trying to correlate the offline campaign to the online activities. So say if I'm a web retailer, I sell shoes, right? And I run a promotion, I send a bunch of emails out. So I want to see, for those people that I send email out, whether they come to my site and actually buy anything, right? So what they're trying to do is correlate the offline with the online activities. So they run this query and they realize that, hey, how come it's taking so long, like to execute a query? And it turns out that when they look at the weblog, so they include the user ID, right? So the problem is they use the same user ID for an anonymous user, like user who goes to the site but they do not logged in, and so over 75% that was the case. So that means we are just hashing 75% of the data to one single leaf node trying to process it. So it's become very, very, very slow. And in reality, they don't really need to care about those users, right? So they change the query statement and just say where user ID is not equal to anonymous, and the query finished right away. So that's a good point. Okay, so I think so when to use it, right? So I think I actually talked about this slide already. So the shuffle step definitely adds some overhead. So it is computation, right? So it will cause poor query performance if used incorrectly. The case that we just said. Okay, so going back to the first example, right? Imagine if you run that query with a group each by, because we know we only have 50 states, right? So if we just hash on 50 states, at most you will have only 50 nodes processing your data. So it's going to be much slower than if you just say group by, because group by you can have a lot more than 50 nodes. No, group by doesn't shuffle. Only group each by. Group each by is relatively new. Join each is new too. Yeah, it's shuffling, yeah. So okay. So basically the rule of thumb is if the number of groups is large, like the example of contributor ID, then you want to use group each by. If it's not large, then you don't want to use it. Okay. So the next topic that we're going to talk about is end-to-end solutions. So this is a fairly typical use case that we've seen. So basically, there's 3 steps in terms of implementing an end-to-end solution. The first step is ingestion, getting the data in, and then the second step is transformation. So, and then the next step is loading the data in the BigQuery, and then the last step is query and visualization. So it's not rocket science, so it's very straightforward. Okay, let's break those steps down in detail. So to ingest data, so there's a couple of ways to do it if you look at the data. So You can actually put the data into the cloud storage first, and then you can run a command to put in BigQuery, or you can actually directly load into BigQuery. But we actually recommend people to use cloud storage first. So there's a couple of reasons. One is if you have to reload your data, it's much faster to go from cloud storage to BigQuery. I guess that's the main reason. So. Okay. So there's two ways to load the data into BigQuery. One is use the putting in the cloud storage. One is use the GS utility, which we used yesterday, or the other one is to use the RESTful API. So there's the common issues with big data. Okay, so when you try to load, say, 1 terabyte data, usually, most likely, you won't run into any problem. Well, 1 terabyte, or say 100 gigabyte. So imagine if you have to load 3 terabytes or 6 terabyte of data. When you have a large data set, you have to plan carefully. So some of the things that you need to think about is, so say if you have multi-terabytes of data, right? How long is it going to take you to upload the data to cloud storage? So you have to consider that, right? So and then so these are different options that you can think about. You can compress your data first, or you can use a third-party data transfer software such as Aspera, or you can establish a network peering with Google, or you can do a hard drive shipment. Okay, so the other thing is I don't know on top of my head, so no. Okay, so for data ingestion, what I'd like to point out is there's some third-party ETL tools such as Informatica or Talent D. So you can actually use those ETL tools, and they can directly import your data into BigQuery. So, but again, if you're talking about 6 terabyte or 3 terabyte, then I would think carefully. Uh-huh.
So when you use those, we use the third-party tools, do they do more than going through TCS and through?
They do a lot more. Like if you use Informatica or Talent or Persuasive, they actually allow you to do data transformation. So, oh, okay.
They do the ENT, the loading part so after you have transformed the data to the part where you like it, the part that they load into BigQuery, do they do more than
No.
TCS?
No. I think most of the third-party tools, they actually use the REST API to go directly to BigQuery.
How
So.
about the fast data transfer? So the third-party high-speed transfer software?
So for the fast data transfer, such as Aspera, they are just strictly data transfer software. They don't do anything with the data.
So how do they achieve a faster transfer?
Okay, so if you use FTP, right? So usually for TCP/IP, it has a handshaking, and then the way TCP/IP is designed. So basically, when you send a package, you have to wait for the ACK, right, to come back, right? So sometimes when the ACK comes back slower, the TCP/IP will throttle it. So what it does is, if I send a package to you and I don't get it within a certain limit, then I'm saying, okay, I'm going to back off. I'm going to send you another package later because I figure that you're busy, right? And so with that protocol, it's not really good for data transfer because at some point I would back off and send you less data, right? So it's kind of varies. So those third-party fast data transfers vendors, they actually bypass that ACK. So they use proprietary protocol. They will just keep sending the data. So they can't utilize the bandwidth much better that way.
So they speed up the portion where they go from, let's say, 9 local storage into TCS. So that part gets speed up. Is that the part that's using this third-party?
Yeah. So if you use third-party software, for example, like Aspera, so what you do is you go to Compute Engine, the GC, you install the Aspera server on GCE, and then yeah, you install your client there. So okay. For ETL, wait, can you use the BigQuery? Should we use BigQuery? Should you use BigQuery as a ETL tool? Oh, you can actually. So, ah, I think that's a hard question to answer because it really depends on use case, right? So it depends on how much data you have, and in my opinion, I think it's actually easier to use BigQuery, right? Because BigQuery support one thing is I think earlier we said the result set has a limit, but actually we added a new feature to allow you to save large data set back into a table. So what you can do is you can load your data, run a query, and then use the features to allow you to store back to your table, right? So you can do that. So, yeah. ASPERA. Okay. So for data processing, basically the common issue is validation, transformation, and denormalization. So what it means is, okay, let's just talk about denormalization first, right? So say if you have data coming from a relational database, and so for relational database, they're highly denormalized. So what BigQuery actually would perform faster if you denormalize the data first. So this is one of the denormalization here. So the other one is transformation. So basically it's changing your data first. Like I think Shiro has a good example. Or the other good example is like if you're collecting log from your mobile phone, right? The mobile phone will give you a lat long, but you want to transform the lat long into maybe a country, or state, or city. So that's an example of transformation. And validation is just make sure your data is good. So for data processing, what we recommend is you can either use the MapReduce from App Engine, or you can use the MapReduce with Compute Engine, or use third-party tools. So loading the data is so loading the data into BigQuery is pretty simple. So you either use the BQ command or RESTful API. Okay, so. Okay, the last step is query and visualization. So there's three ways that you can query your data. You either use the BQ command or web UI or the RESTful API. And the common issues that you will see is the result set too large. So I think Shiro mentioned that. The other one is resource exceeded during query execution. So this is most likely is because you're trying to do a group by instead of group each by. So if you see this one, then you have to change the group by to group each by, or join to join each. So okay. So before I talk about this end-to-end solution, so one of the common problem that we see from our partners is quota. I think a lot of people don't realize that there's a quota. So the most important point to remember is because BigQuery is a shared service, right? When you submit your query, we have a farm of server to execute the query, right? And if the other person submit a query, it's the same farm of server that handles the query. So we actually have quota to make sure that nobody is hogging about the resources. So we have quota regarding the number of query you can run a day. We have quota regarding the number of load jobs you can run a day. We have a different quota. So when you design your data pipeline process, make sure that you keep those quota in mind. So if you're expecting 100 records a second and you're thinking that you can just store each record into BigQuery, you're going to run into the quota problem pretty soon. Okay, so I like to conclude with an end-to-end example. So this is So this is a real customer. So they actually did a very interesting use case for BigQuery. So what they are doing here is they're trying to understand the consumer's buying pattern and the effect of weather. So what they did is they get 3 years of data from a big grocery store, and then they matched it up with the weather data, and then they try and analyze what people buy and what people buy more and buy less. So before using BigQuery, they were not able to go down to the line item level. So they would roughly know at the category level, people buy more, maybe perishable food or perishable food. So with BigQuery, they were able to look at the line item level. So that was really cool. So when I was talking to them, so they just asked me this trivia. Is that so? Right before a big storm hits, do you think people buy more beer or wine? Okay, who think it's beer? Okay. Who think it's wine? Okay. Who likes to drink warm beer here? Warm, like. If you don't live in the Midwest, right, you don't know a lot of times when there's a big storm, sometimes you lose power, right? So when you lose power, you cannot keep your beer cold. So the answer is wine. Okay, so that concludes this session. Okay.